going to be much less theoretical. So we're just going to be kind of moving straight ahead. So we're going to continue talking about sets, and we're going to talk about another special kind of set called a relation. So a relation is a set of ordered pairs where the x values are coming from a set D and the y values are coming from a set R. When we say ordered pairs, we're talking about like a coordinate, like an x comma y, like you dealt with in geometry. We call the set D the domain, and we call the set R the range. So let's look at like a concrete example just to kind of reinforce what we're saying here. So a relation is a set, so I'll just name it with a capital letter, say the capital letter A. And then we'll use our squiggly bracket. And then I'll list, this will be a finite relation. So I'm just going to list the ordered pairs that make up this relation. So there's just a set of ordered pairs. Everybody okay there? So for this relation, what would we say the domain is? So there are the x's, so that would be 1, 3, 5, and 7. Everybody's okay there? The range is just the y's, so the range would be 2, 4, 6, and 8. Everybody okay with that idea? So we might ask ourselves, is 1 a member of the set A? Is 1 part of that relation? What do you say here? Anybody with an opinion? The answer here should be no. Remember that a relation is a set of ordered pairs. So the things inside the relation are ordered pairs. 1 is not an ordered pair, right? However, 1 is a member of the domain. Okay with that? If we wanted something in A, we would need an ordered pair. So, for example, the ordered pair 1, 2 is a member of A. Again, remember this little symbol here, this curvy E, is just our notation for like a member of a set. Now, since a relation is just a kind of a set, Relations can be finite or they can be infinite. This one here is a finite relation. And just like we discussed last time, the notation that we use to represent a finite set and an infinite set is slightly different. So let's look at an example of an infinite relation, because the finite ones are usually pretty easy to deal with. It's just going to be a list, right? The infinite ones can be a little bit trickier. So here's an example of an infinite relation. So what does all these symbols kind of mean in words? Let's kind of talk through it again so we get comfortable like reading the notation. So this says B is the set of ordered pairs such that the x-coordinate is equal to the y-coordinate, and those x and y coordinates are real numbers. So what's an example of an ordered pair that is in this relation B? Go ahead. 1, 1. Excellent. That's an ordered pair where the x and y coordinate are the same. Everybody's okay with that? What's an example of something that's not in this B? Yes, sir.
1, 2.
Excellent. 1, 2. So anything where the coordinates are different. Do we feel okay about that? So it's, again, very similar to the set notations we looked at yesterday, but this time we have x and y's, right? So we need a way to relate the x and y's together, typically in our rule. Okay. So there are 4 ways that we typically use to represent a relation. The first of those ways is as a set of ordered pairs, just like we saw before. So I'm not going to do a new set of examples. We just did sets of ordered pairs there as the basis for our definition. So there's not much more to say about that. Note that here we can do this with finite or infinite relations, right? The next way to represent a relation is with something called a mapping diagram. And really, because of the nature of the mapping diagram, this is really good for finite relations only. So with a mapping diagram, what we do is we're going to draw 2 ovals, one for the domain and one for the range. And then we're going to write in the items that are in either the domain, and then the items that are in the range inside those ovals. And then we're just going to draw arrows to indicate how the ordered pairs are made. So each one of these arrows would represent an ordered pair. To just kind of give you an idea, translating this back to a set of ordered pairs so you guys can see, get a good idea of what this is saying. So this arrow here represents the ordered pair 1, 0. This arrow represents the ordered pair 1, 2. This arrow represents the ordered pair 2, 3. And then that last arrow represents the ordered pair 3, 0. Is everybody okay on that? We can see how to read that mapping diagram. Okay. The next way is with a graph. This is good for both finite or infinite. So if I'm graphing a finite relation, I'm just going to have some points. Now I want to be clear here. If you have a finite relation, your graph is going to be just points. The reverse is not necessarily true. You can have an infinite relation that is just made up of points. We'll look at an example here in a second. But if your relation has only points, it's guaranteed to be finite. Nope. If your relation is finite, it's guaranteed to have only points in it. Nothing connected. Now, if your relation is infinite, it's going to have some kind of segment, connected section in it, like some kind of line segment. Remember in geometry, one of your axioms, like one of the very first things you talked about in geometry, is that a line is made up of infinitely many points. So anytime you have a connected piece on your graph, that contains infinitely many points and automatically makes the relation infinite. So if you have any kind of connected segment on your graph, it's going to be an infinite relation. However, there are some infinite relations that don't have any connected pieces to it. So let's look at one more example here. That is infinite but has no connected pieces in it. So this looks very similar to the infinite relation that we talked about at the beginning, right? What's the only difference between that one and this one? Yeah, the set that the x and y's are coming from is the integers as opposed to the real numbers. Why is that going to make a difference? Well, for example, in this set, or in this relation, 1, 1 is a point, 2, 2 is a point, but nothing, there's no points in between those, right? 0.5, 0.5 isn't a point in this relation, where it was in the previous one, right? So here, I'm going to have 0, 0, 1, 1, 2, 2, 3, 3, on and on and on. And similarly, negative 1, negative 1, 1, negative 2, 2, negative 3, 3, and on and on. I have infinitely many points, But none of them are connected, right? Because the integers, there's no numbers in between like 1 and 2. You guys see that? So here's an example of a relation that's just points, but is still infinite, right? Now, if there's a connected segment, we know it's infinite. If we know it's finite, we know it's just points. But if all we know is it's just points, we don't know for sure if it's finite or infinite, right? So just to be clear, a lot of times it's easy to go, oh, these two statements are equivalent, and they're not quite, right? They're not quite. All right. The last representation is as an equation. And for practical purposes, this is really infinite only. So for example, something like y equals 2x plus 5 is an equation that represents a set of ordered pairs, right? This is something that we learned how to graph in previous classes. You can generate infinitely many ordered pairs using this rule. Those would be the ordered pairs that would be in our relation. Is everybody okay with that idea? Okay. Good. So now we're going to define a special kind of relation. Called a function. So a function is a relation where every member of the domain pairs with exactly one member of the range. So if I want to determine if something is a function, there's three things I need to check. I need to check first that it's a relation. It has to be a set of ordered pairs. Second, everything in the domain pairs to something. And then third, that each of those members in the domain only go to one thing. So let's look at some examples here. So I'm going to do a whole bunch of examples. Like, I don't know, 15 or 20 of them probably. So we're going to decide if this is a function or not. And then we're going to list the domain and range. So why am I going to do so many examples? Because there's 4 different representations that I can have for a relation. So there's 4 different, like I have to do some examples from each of those different representations, and they just kind of add up. Everybody's okay with that plan? Okay. Okay. So first thing, let's decide whether this is a function or not. Remember, there's 3 things to check. Is it a relation? Yeah, that's just a set of ordered pairs. That's fine. That's one of the representations we use for a relation. That'll work. is everything in the domain paired with something in the range? Yes, because again, we have ordered pairs. If you have a set of ordered pairs, that part is trivial. The last thing we need to make sure is that everything in the domain pairs with exactly one thing in the range. Is that going on? Yes. So basically, I'm just looking to make sure that each of my x coordinates are unique, which they are. Okay, so we can conclude this is a function. The domain is 1, 2, 3, 4. What's the range going to be? 2, 3, 5, right? Why didn't I list the second 2? Right. Remember, the definition of the set is that the items are non-repeated. So I cannot list the 2 a second time. Can only occur once. I would mark down on a test or quiz if you listed a set with more than one or with repeated elements in it. Everybody okay there? Okay. Oh, you know what? Let's not do an infinite one yet. I'm sorry. Let me do another example here. Okay. Is this a function? You say no. Why not? Good. Right? Because the domain of 1 is pairs with 2 separate y values. I have 1 going to 3, or 1 paired with 3, and then also 1 paired with 4. Everybody's okay with that? Did it matter that the y value of 3 pairs with 3 different x's? Not in determining if it's a function or not. Good. The domain should be what? Yeah, just 1, 2, 3. Very good. And the range then would be 3, 4. Okay, so let's look at this one. A little bit harder looking at this immediately and telling if it's a function or not, right? So maybe we come back to this idea after we do something else. My suggestion on these infinite sets of ordered pairs, we're going to translate it into a graph and then use what we know about the graph to deal with it. Because when you look at this, it's not entirely clear, and there's not a good way of approaching it without kind of basically translating it to a graph. So let's just kind of come back to that one. Someone's got to remind me to do it, though, because I'm going to forget between now and then. Well, actually, let's just do a graph right now. Why not, right? I don't have to go in the same order that they were listed there. Does this represent a function? Is it? Okay. You say no. Why not? Very good. So, I don't have the seating chart for this class. What's your name? Alyssa has pointed out to us these 2 points on the left would have the same x coordinate, right? Because they appear on the same vertical line. Everybody agree with that? Informally, we call that the vertical line test. Oops. I don't know why I said a function there. I meant a graph. Okay, so the vertical line test says that if you can draw a vertical line that intersects a graph more than once, that graph does not represent a function. Oh, we didn't talk about the domain and range for this one, though. Let me time out here for a second. I'm going to do this to make myself a little bit of space to do that. Now, from the information I've given you, can you do the domain and range for this problem? No. What do you need? The coordinates for the points, right? In which case, after you had that, it would be easy. Agreed? Okay, so I'm going to not actually write any coordinates in because it's just kind of a big waste of time. But we didn't talk about it, so I want to make sure we go back and everybody's clear as to, like, if you had the coordinates for the points, could you do this? And then the answer hopefully is yes, right? Okay, now let's look at E. Is this a function? Can I draw a vertical line that intersects it more than once? Doesn't look like it, right? No matter where I draw that vertical line, it's only going to get the graph 1 point. You guys agree? Now these ends, you might say, oh, they look vertical. They're just really steep. And maybe you can't tell that from my crappy picture, but that's a fair comment. If you're like, the ends, they look vertical. I didn't mean to draw them so they look vertical. They're just supposed to look steep. Is that okay? Okay. All right. What's the domain going to be here? This is a little bit trickier, right? Oh, sorry. I wrote the wrong thing. Thank you. No, you're correct. Again, if I write something and it doesn't make sense to you, it's possible I make mistakes. It does happen. Thank you for asking about it. This is absolutely a function. Okay. So this is an infinite relation, right? So I have infinitely many points. That means I'm going to have potentially infinitely many x's or y's, right? So we're probably going to want to use like an interval notation or something here to describe the domain. You guys agree with that? Okay. So the first thing I'm going to ask is this graph continuous? That is, can I trace along the curve without having to pick my finger up? Yes. So in which case it tells me I can just do this with one interval for a domain or range. If I had to pick up my finger, I'm probably going to need more than one interval. Okay with that idea? So I'm going to ask myself then, what's the smallest x value used in a point on this function? Well, I have an arrow that points down and to the left, which tells me that the smallest x value is going to be negative infinity. Is everybody okay with that? And since it's a infinity, I'm going to start with the parenthesis already for my interval notation. What's the biggest x value then? Positive infinity, because I have an arrow pointing up and to the right. Yes? So you could say, or the set of x is such that negative infinity is less than x, which is less than positive infinity. You could represent it that way. Or even just like as an inequality. Any of those representations I would accept. Okay? What should I, or now it's up to range, right? So what's the smallest y coordinate? I have an arrow that points down, so it's going to be negative infinity. And the biggest y coordinate? Positive infinity. Or you could represent it the same, since it's the same interval, you could represent it the same way as those previous ones, right? Everybody's okay with that? Okay. Let's circle back now to that one that we skipped, because I think at this point now we've done enough to where we can deal with that guy. So let's scoot back up to C. So if I want to sketch a graph for C, this is the piece that I'm going to be primarily interested in, is the rule that describes how the x's and y's pair together. Does anybody recognize the shape of that, or the shape of the graph that that equation would give us right off the top of their head? Well, I heard somebody say it. Parabola, right? It's going to look like a U. How many of us would have gotten there with just prior knowledge, given another minute or two to think about it? Nobody wants to volunteer that would have been done? Okay. So, otherwise, if not, you can just kind of do some test cases. So like you could just pick some values for x and kind of see what's going on. If you do that, you can then plot some ordered pairs and get an idea of what the graph is going to look like. Now notice I connected this all the way through. How did I know that this graph was going to be connected? Because x was coming from the real numbers. And the real numbers are all like, you can get as close as you want to the next one, right? Between 1 and 2 contains every decimal between 1 and 2. So all those points are going to be continuous, connected. Is everybody okay with that idea? Okay. All right, so this is my graph. Is this a function? Yes, right? Definitely passes a vertical line test. Okay. The domain is easy because it's basically just given to me here, right? If x can be any real number, well, then my domain is just going to be negative infinity to positive infinity. There's nothing really to assess there. Is everybody okay with that? Yes. That's the member of a set symbol. That's like the curvy E. Again, that's probably mostly just my crummy penmanship. You knew it once I said it. You're like, oh, that symbol that normally is written much nicer than that. It's okay. Yeah, it does look like any number of like a lowercase t or something else. I don't know. Like, could be lots of things. It's bad penmanship on my part. The range, though, is not going to be the same as the domain here, right? What's the smallest y-coordinate we can have? 0. And what's the biggest? Positive infinity, because we have arrows that point up. We know the infinity gets a parenthesis. Should the 0 have a bracket or a parenthesis? Well, do I have an ordered pair that uses 0 as its y-coordinate? Yes, right? I just circled it. So that means that 0 gets a bracket. Because there is a point on my function that actually has that y-coordinate, right? The y-coordinate 0 gets used by my function. 0 is in the range. Everybody okay with that? Okay. Let's do another. C, D, E, F. So this one, we have this diagonal line and this extra point. Yes, sir. Not a function. Good. Why? Yeah, what vertical line can I draw? Yeah, so it has to be going through that dot, or the extra point. And in fact, that's the only vertical line we can draw that would intersect the graph more than once. But there only has to be one line. Good. Who can tell me what the domain is going to be for this? So I have the arrow pointing to the left. Yes. It's good. It is negative infinity to positive infinity because I have the arrow that points to the left and the arrow that points to the right, and it's connected all the way in between. That's going to tell me that it's negative infinity to positive infinity. Is everybody okay there? Okay. What's the range going to be? What'd you say? Oh, there's a range. Does the dot matter? Well, whatever y-coordinate is on that dot is already on the line. So the dot doesn't really matter to us, right? Because that y-coordinate is already on the line. Very good. It would also be negative infinity to positive infinity. In general, if you have an arrow pointing up and an arrow pointing down and it's connected in between, then it's going to be the same thing, negative infinity, positive infinity. Let's look at an example where maybe the range gets weird. E, F, G. Or the domain, or both. Okay, so let's do something sneaky here. Okay. Is this a function? No, why not? Where can I draw the vertical line through? Yeah, x equals 1, right? That's the only spot, though. No, because what's the open circle mean? Means that point is not included, right? Goes butts up right to it. For example, negative 2.999999999 is a point, but negative 3, 1 would not be. Is that okay with everybody? So that was left not filled in for a reason. It meant something. But I'm glad you asked, because it gave us an opportunity to review that little notational thing, what that means. Yes, sir. Good. Yeah, so the domain is, still also negative infinity, and the range is still, or negative infinity, positive infinity, and the range is still the same. Good. So for the domain, I have everything from negative infinity to negative 3 there, right? And then I have everything from negative 3 to positive 1. And then I have everything from positive 1 to positive infinity. I didn't skip anything. So the domain is negative infinity, positive infinity, right? If I do the range, I have negative infinity up to negative 1. And really, I don't even care about this piece in the middle, because this section has everything from negative 1 to positive infinity. So I have everything in for the range as well. So you can still get a domain or range that's negative infinity to positive infinity, even if the ends of the arrows are not connected. Everybody's okay with that? Okay. Do you want to do some more like that? Is that helpful? We can do a couple more. We have time. Right? We're doing pretty good. What do we still have? 10 to 15 minutes. Yeah, I still have to talk about equations, but we can do one more. A, B, C, D, E, F, G, H. Those are open circles. Yep. Perfectly reasonable question. My penmanship is, it is what it is. Right? Okay. I could have probably reduced this down and did not included so many of these little. So this is a function. Yep. Good. It passes the vertical line test because the place in question would be situations like that, but one of the circles is closed and one is open, so it's just one intersection, so we're okay there. Does everybody agree with that? Okay. What's the domain going to be? So the domain is actually infinite. It's not finite. Because we have everything from -4 all the way to -3. Right? Remember, the domain is the x rather than the y. So what's the domain going to be? What's the smallest x involved? -4. And it goes all the way to, it goes to -3, but then we have -3 to -2. That should be a -2. And then we have everything from -2 to -1. So we're really starting at -4 and ending at 3, right?
So we use the open circle.
Well, it's okay because the same x value. Here. Is that okay? So basically, if I take all of these guys and just squish it all down to a number line, I would start here, and everything is get covered up until the very end. Does everybody kind of see that? If I just kind of squish that all down onto one line, that the open circles get filled by the closed circle that's directly above it. Everybody kind of see that now? That's maybe a nice way to visualize this. So the -4, parenthesis or bracket, and the 3 gets a parenthesis because it is open still at the end. Yes. Good question. And then you'd use a parenthesis if the endpoint is open. Yep. Good question. And now, is it the, wait, hold on, no. Is it Mackenzie that you were, okay, what's the range now? Now remember, the range is the y's. Okay, you're close. Is the range infinite or finite? So if we squish these now down this way, instead of squishing to the x-axis, if we squish to the y-axis, all you have is points, right? So the range is going to be finite. It's just going to be those, 7 points. Do you guys see that? Now that's quite tricky. Right? You have a domain that's infinite and a range that's finite. Yes, sir?
Why would the domain be infinite again?
So if you're looking at the x values, even just right here, we have infinitely many different x's, right? Because on this little segment, we have every number between -4 and -3. But if I look at the y-axis, all of these have the same y-coordinate, right? They're all just -3. And then I don't have any other different y-coordinates till I get up to here, but they're all at -2. And then I don't have any more y's until I get up to here, and those are all at -1. And so on and so on and so on. The y's are just jumping. The x's are continuous along that. As we go from left to right, we cover all the x's, but the y's, we just have these discrete jumps. Sneaky. Does that feel better?
Yeah, I was just confused with why it was infinite, you don't necessarily go on. Like,
Oh, yes. So it's a line segment, but the segment, remember, has infinitely many points. Yeah. Yep. Okay, let's do some equations here to finish up. J. Is this a function? Translate it to a graph. What's the graph look like? It's just this, right? Doesn't even matter if you have like the slope or the points or anything really close. All you need to know is it's a non-vertical line, right? So that's a function. And we know that just by looking at it because it's in y equals mx plus b form, right? What's the domain going to be? Good. And the range? The same thing. Yeah. How about this one? Do we know what this is going to look like straight away? Well, which way is it facing, though?
Yeah.
It might not be clear. Let's start by doing this. Let's get the y by itself. Typically, everything, if we're going to try to translate this to a graph, everything gets a little bit easier if we get the y by itself. Everybody okay with that plan? To get the y by itself, what do we need to do? Square root both sides. When we square root both sides of an equation, what do we generate? Plus or minus. And now, right now, I think that we can probably, without even graphing this, make some distinction here, right? For example, if I just pick x to be 1, that tells me that y has to be plus or minus 1. So that generates the points 1, 1, and 1, -1. So what can we say here? Not a function, right? Was everybody okay with how I got y to be plus or minus 1 so quick? The square root of 1 is 1, so you just have plus or minus 1. And you plugged in x to here. Okay. So let's use those 2 points . And we know if x is 0, y is obviously 0. And certainly x we can't choose to be negative. So your parabola that you're expecting is actually opening to the right rather than upside down. which was maybe I think somebody said was their initial thought, which is, again, not a bad thought. Like that you realized it was going to be a parabola, which is excellent, right? The orientation of that parabola, maybe not clear from just looking at it. Okay, so the domain. You can cheat a little bit here. If we went back and looked at this one, what would I expect the domain and range be for the one that I'm currently studying? Switched, right? Since the parabola is lying on its side, both arrows are pointing to the right. So the domain is going to look like this one's range, and the range is going to look like this one's domain. Do you kind of see that on how I cheated there to get it? You could do the same thing, though, that we had been doing before here as well by saying, okay, the smallest x is here at 0, and the biggest x goes off to positive infinity. And because I do have a point here at 0, 0, that value gets a bracket. In the range, we have an arrow pointing up and an arrow pointing down, and it's connected in between. So it should be positive infinity, or negative infinity, positive infinity. Okay, so today we've done enough for you guys' first homework assignment. You can get that first homework assignment. It's attached to Power School. If you look at Power School, there's a homework assignment there. I'm also going to put the handout in the content library so you can get it from either place. If you want to do all your work in OneNote, that's fine. If you want to do it on a separate sheet of paper, then dump it into OneNote afterwards. The picture, that's fine. The due date for the homework, so, is Sunday at midnight. So you have a good chunk of time still to kind of pick away at that. Anybody with questions before we finish up here? I'm feeling